Think about the last time you looked up at the night sky and felt that deep, almost primal sense of wonder. Those tiny pinpricks of light, each one a sun, a world, possibly even a home to civilizations we can't even fathom. The universe is vast beyond comprehension, filled with secrets that defy logic and truths so strange they seem ripped from science fiction. But here's the thing, reality is often far more bizarre than anything we could invent. What if I told you that everything you think you know about space, time, and even the fabric of existence might be wrong? Take this for starters. Right now, you're hurtling through space at over 1,000,000 miles per hour. Not just Earth, but you sitting there, are on a cosmic roller coaster with no brakes, and that's just the beginning. The universe is stranger than we've ever imagined, hiding truths so shocking they'll make you question the very nature of reality. Black holes that warp time like taffy, invisible dark matter holding galaxies together, parallel universes where every decision you've ever made plays out in infinite variations. These aren't wild theories, they're real, measurable phenomena, and they're just the tip of the cosmic iceberg. That's why we're diving deep today into 30 of the most mind-bending truths about the universe. Some will sound like pure fantasy, others might unsettle you, make you feel small in the grand scheme of things, but also connected to something unimaginably vast. By the time we're done, you'll see the cosmos in a whole new light, and trust me, you'll never look at the night sky the same way again, so buckle up. We're about to explore the edges of reality itself, where the rules you know don't always apply, and the universe reveals just how little we truly understand. Ready to have your mind blown? Let's begin. Here's something that will make your head spin. Nearly everything in the universe, the stars, the planets, even you, is just a tiny fraction of what's actually out there. In fact, the stuff we can see, touch, and study, that's only about 5% of the cosmos. The rest is an invisible mystery, a cosmic shadow world made up of dark matter and dark energy. These two forces are the hidden architects of the universe, shaping everything from the smallest galaxies to the fate of reality itself, yet we've never directly seen or touched them. Dark matter is like the universe's silent scaffolding. We know it's there because galaxies spin so fast that they should tear themselves apart, unless something unseen is holding them together with gravity. Picture a merry-go-round spinning wildly, but instead of flying off, the riders stay glued in place. That invisible grip, that's dark matter. Without it, galaxies would disintegrate, and the cosmos as we know it wouldn't exist. Then there's dark energy, an even stranger force pushing the universe apart at an ever-increasing speed. Think of it as anti-gravity, stretching space itself like an inflating balloon. Every second, more of the universe slips beyond our reach, driven by this mysterious energy. And here's the kicker, we have no idea what dark energy actually is. It doesn't just hide in the shadows, it's rewriting the rules of physics as we speak. So why can't we detect these cosmic phantoms? Because they don't interact with light or matter the way normal stuff does. They're ghosts in the machine, leaving only faint fingerprints, like the way gravity bends light around galaxy clusters, or how distant supernovas appear dimmer than they should. Scientists chase these clues with massive detectors buried underground, telescopes scanning deep space, and experiments that sound like sci-fi. Yet after decades of searching, dark matter and dark energy remain two of the biggest unsolved puzzles in science. What's wild is how these invisible forces dominate the universe, while everything we've ever known, every mountain, every ocean, every human, is just cosmic afterthought, a sprinkling of stardust in an ocean of shadow. It's humbling, sure, but also thrilling, because somewhere out there the answers are waiting, and uncovering them could rewrite our understanding of existence itself. Time doesn't tick the same way everywhere in the universe. It bends, stretches, and warps depending on where you are and how fast you're moving. This isn't science fiction. It's Einstein's theory of relativity in action, and it's as real as the ground beneath your feet. Imagine two identical clocks, one placed on Earth's surface, the other launched into space aboard a satellite. After a while, you'd find the space clock has actually ticked faster than its Earth-bound twin. That's not a glitch, it's physics. The closer you are to a massive object like Earth, the stronger gravity's grip and the slower time crawls. This effect isn't just some abstract curiosity, it's the reason your GPS works. Satellites orbiting high above Earth experience time slightly faster than we do down here. Without accounting for this difference, your phone's navigation would be off by miles within minutes. Engineers have to tweak the satellite's clocks to compensate for relativity, or your road trip would turn into a cosmic wrong turn. But here's where it gets even weirder. Speed also warps time. The faster you move, the slower your clock ticks compared to someone standing still. Picture twins. One stays home while the other rockets through space at near light speed. When the traveling twin returns, they'd be younger than their sibling, maybe by years, depending on the journey. This isn't hypothetical. Atomic clocks flown on airplanes have measured the difference down to tiny fractions of a second. What's truly mind-blowing is that time isn't some universal metronome. It's more like a river flowing at different speeds depending on the landscape. Near a black hole where gravity is crushing, time could slow to a near standstill. Meanwhile, in the empty void between galaxies, it might race ahead unfettered. This means the past, present, and future aren't fixed. They're fluid, shaped by where you are and how you're moving. So the next time you glance at a clock, remember, it's not just measuring seconds. It's telling your time in your corner of the universe, and somewhere out there in the cosmic deep, time is dancing to an entirely different beat. Try wrapping your mind around this. If you scooped up every single grain of sand from every beach, every desert, every hidden corner of Earth, you'd still have far fewer grains than there are stars in the observable universe. That jaw-dropping fact isn't poetic exaggeration, it's cold, hard math. Our Milky Way alone holds roughly 100 billion stars, each a blazing sun with its own possible planets, moons, and stories. Now zoom out. Astronomers estimate there are at least 2 trillion galaxies beyond ours, each brimming with hundreds of billions of stars of their own. The numbers quickly spiral into the unimaginable. Picture standing on a shore at night, holding a handful of sand. Those tiny grains slipping through your fingers might number in the tens of thousands. Now look up. Every speck of light you see isn't just a star, it's an entire beach worth of stellar bodies. The scale becomes absurd when you realize some of those stars are actually galaxies themselves, each one a swirling island of billions more suns. The universe doesn't just dwarf our planet, it makes Earth's grandest numbers feel laughably small. Here's another way to grasp it. If every grain of sand on Earth represented a single star, you'd need over 10,000 planets just as sandy as ours to match the cosmos's star count. And that's only counting the observable universe, the portion we can see. Beyond that, space might stretch infinitely, filled with more stars than any human could ever conceive. Yet amid this cosmic ocean, each star is its own marvel. Some burn blue and fierce, dying young in spectacular supernovas. Others, like our steady sun, hum along for billions of years, nurturing life. And then there are the red dwarfs, faint but stubborn, outliving every other star type by trillions of years. The diversity is staggering, and it's all happening right now across distances so vast they defy comprehension. So next time you're near sand, kicking it at the playground, feeling it between your toes, remember, you're standing on a speck of cosmic dust, adrift in a sea of fire and light so vast it redefines what countless even mean. The universe doesn't just contain wonders, it operates on a scale that turns wonder into pure, humbling awe. Here's a cosmic fact that feels almost impossible. The moon is slowly but surely leaving us. Right now, as you read this, our closest celestial neighbor is drifting away at roughly 3.8 centimeters every year, about the speed at which your fingernails grow. It's not much in a human lifetime, but over millions of years, that tiny gap adds up to something staggering. And the reason behind this quiet escape isn't some distant force, it's the same tug of war that gives us ocean tides. Every time the moon's gravity pulls on Earth, it creates bulges in our planet's oceans. But because Earth rotates faster than the moon orbits, those tidal bulges actually get dragged slightly ahead of the moon's position. That off-center pull transfers energy, nudging the moon into a higher orbit while simultaneously slowing Earth's rotation. Think of it like a cosmic figure skater extending their arms. The moon moves outward as Earth's spin loses momentum. Now fast forward 50 million years, the moon would appear noticeably smaller in the sky, and total solar eclipses, those breathtaking moments when the moon perfectly blocks the sun, would become a thing of the past. The moon's apparent size would shrink just enough that it could no longer fully cover the sun, leaving only partial or annular ring of fire eclipses. Eventually, hundreds of millions of years from now, Earth's day will stretch longer too. Right now, we rotate once every 24 hours, but as the moon siphons off Earth's rotational energy, days could grow to 25, then 30 hours, a sluggish, alien rhythm compared to the world we know. Here's the twist: this isn't a one-way trip. The same physics that's pushing the moon away also ensures it will never truly leave us. At some point, billions of years from now, Earth's rotation will slow enough to match the moon's orbit, locking the two in a gravitational embrace. They'll become tidally locked, always showing the same face to each other, just like the moon already does with Earth today. By then, the moon will have retreated to about 1.5 times its current distance, and Earth's days and months will stretch to the same length. So while we won't be around to witness it, the dance between Earth and the moon is far from over. It's a slow, relentless waltz dictated by the laws of physics, one that's reshaping both worlds in ways we're only beginning to understand. The next time you gaze up at the moon, remember, it's not just a silent companion. It's a traveler gradually carving its path through space and time, leaving its mark on Earth's future with every centimeter it gains. Some of the most terrifying objects in the universe also create music. And not just any music, but a deep, haunting hum that would send chills down your spine if you could hear it in space. In 2003, astronomers made an astonishing discovery. A supermassive black hole at the heart of the Perseus galaxy cluster was emitting sound waves. Not metaphorically, not poetically, actual pressure waves rippling through the scorching gas surrounding the black hole. And when scientists translated those waves into audible frequencies, they revealed a tone so low it's 57 octaves below middle C, a bass note that would make even the deepest pipe organ seem like a whisper. Here's how it works. As the black hole devours matter, it doesn't do so quietly. Enormous bursts of energy erupt from its accretion disk, the swirling vortex of superheated gas and dust spiraling toward oblivion. These explosions send shockwaves through the surrounding plasma, like dropping a boulder into a thick cosmic pond. The waves propagate outward, compressing and rarefying the gas in a rhythmic pattern. But there's a catch. Space itself is mostly vacuum, so these sound waves can't travel like they would on Earth. Instead, they move as pressure variations in the sparse intergalactic medium, a ghostly vibration detectable only with the most sensitive X-ray telescopes. NASA Chandra X-ray Observatory captured these waves, and when researchers scaled them up by quadrillions of times to make them audible, they revealed an eerie drone, a single sustained note echoing across 250,000 light-years. Imagine the deepest sound you've ever heard, then go deeper, so deep it vibrates your bones more than your eardrums. That's the voice of a black hole, a sound so low it would take a human 15 trillion years just to sing one cycle of it at its original frequency. What's even wilder, this isn't unique. Many supermassive black holes likely sing, their voices too deep for any human to perceive naturally. Some might even harmonize their gravitational pulls, weaving intricate patterns in the fabric of space-time. It's a reminder that the universe isn't silent, it's a symphony of forces, from the faintest electromagnetic whispers to the roaring crescendos of colliding galaxies. And somewhere out there in the darkness, black holes are humming the oldest songs in existence. Even in the deepest, emptiest reaches of space, there's no such thing as absolute cold. The universe itself has a temperature, a faint, uniform warmth lingering from its fiery birth. This afterglow, called the cosmic microwave background, is the oldest light we can detect, a whisper from 13.8 billion years ago when everything began. Picture the Big Bang not as an explosion in space, but as the sudden expansion of space, a blistering hot soup of energy and particles. As the universe expanded and cooled, that primordial light stretched into microwaves, fading but never disappearing. Today, it bathes every corner of the cosmos at a frosty 2.7 Kelvin, just a hair above absolute zero. Detecting this ghostly echo wasn't easy. In 1965, two radio astronomers named Arno Penzias and Robert Wilson stumbled upon it while troubleshooting a persistent hiss in their antenna. No matter where they pointed it, the noise remained like static from an invisible TV channel. At first, they blamed pigeon droppings on their equipment. But after scrubbing the antenna and chasing every possible explanation, they realized they'd found something extraordinary: the faint thermal fingerprint of the Big Bang itself. That discovery earned them a Nobel Prize and reshaped our understanding of the universe's origins. What's mind-bending is how perfectly uniform this background radiation appears almost. Tiny fluctuations in its temperature, mapped by satellites like the Planck Observatory, reveal the seeds of all cosmic structure, those microscopic hot and cold spots. They're density variations from the early universe, the gravitational blueprints for galaxies, stars, and everything we see today. Without those imperfections, matter would have spread evenly, and the cosmos would be a featureless void. Instead, those slight temperature differences, some as minuscule as 1 part in 100,000, became the scaffolding for reality as we know it. Here's where it gets even stranger. Because the cosmic microwave background is everywhere, it technically means no place in the universe is truly empty or cold. Even in the vast voids between galaxies, where darkness seems absolute, space hums with this remnant heat. It's a reminder that the universe isn't just around us, it's in us too. The atoms in your body were forged in stars, but the warmth in the void, that's the echo of creation itself, a cosmic hearth cooling slowly but never quite going out. So the next time you step outside on a cold night, remember, the chill you feel is nothing compared to the deep, ancient cold of space, but even there, the embers of the Big Bang still glow. Right this second, as you watch this video, trillions of invisible particles are shooting through your body like you're not even there. No, this isn't science fiction, it's the bizarre reality of neutrinos, the universe's most elusive ghosts. Born in the nuclear furnaces of stars, supernova, and even the Big Bang itself, these subatomic phantoms barely interact with anything, making them cosmic ninjas that slip through planets, mountains, and you without a trace. Take the Sun, for example. Every second, about 65 billion neutrinos from its core pass through every square centimeter of Earth, including you. That means in the time it takes to blink, billions have already zipped through your hand, your coffee cup, even the floor beneath you. And here's what's wild, nearly all of them leave no evidence. Unlike light or radiation, neutrinos don't scatter electrons or break molecular bonds. They're so indifferent to matter that a neutrino could fly through a light year of solid lead. That's 6 trillion miles without hitting a single atom. So how do we know they exist at all? Because very rarely one gets caught. Deep underground, in tanks of ultra-pure water or liquid argon, scientists wait like cosmic anglers for that 1 in a quadrillion chance a neutrino bumps into an atomic nucleus. When it happens, the collision releases a faint flash of light or a ripple of charge, betraying the particle's presence. The most famous detector, Japan's Super Kamiokande, is a massive cavern filled with 50,000 tons of water, surrounded by sensitive photodetectors. It's like trying to catch a single firefly in a dark stadium by waiting for its wings to brush against one specific grain of sand. What makes neutrinos even stranger is their ability to shapeshift. As they travel, they oscillate between three different flavors: electron, muon, and tau neutrinos, switching identities like undercover agents. This chameleon act proved neutrinos have mass, appending physics models that assumed they were weightless. Yet their mass is so infinitesimal that it's still not precisely measured. They're the lightest known particles with mass, billions of times lighter than electrons, making them cosmic feathers drifting through space. Some neutrinos aren't just solar leftovers, they're interstellar messengers. When a star explodes as a supernova, 99% of its energy bursts out as neutrinos, carrying secrets about dying stars. In 1987, detectors caught 24 neutrinos from a supernova in the Large Magellanic Cloud, 3 hours before telescopes saw the light. Those particles had raced ahead, unimpeded by the star's collapsing layers, while light lagged behind, struggling through the cosmic fog. Here's the kicker: right now, your body contains about 20 milligrams of potassium-40, a radioactive isotope. As it decays, it shoots out neutrinos, meaning you're not just a neutrino bystander, you're a neutrino factory. Every atom in your body is part of this silent subatomic exchange, woven into the universe's most pervasive yet invisible conversation. So the next time you feel alone, remember, you're constantly flooded by particles older than the sun, quieter than thought, and faster than light can travel through water. They're the universe's subtle whisper, a reminder that even in stillness, you're immersed in a cosmic dance most of us will never see. Imagine a hole in the universe so vast it could swallow thousands of galaxies without a trace, yet it's almost completely empty. This isn't some sci-fi plot twist, it's the Boötes void, a cosmic emptiness so staggering it defies logic. Stretching 330 million light-years across, this spherical desert of space contains fewer than 60 galaxies. To put that in perspective, a region that size should host around 2,000 galaxies based on the average density of the universe. But here, the stars have all but vanished, leaving behind a yawning abyss that astronomers still struggle to explain. What makes the Boötes void, sometimes called the Great Nothing, so unsettling isn't just its size, but its existence. Space isn't supposed to have gaps this extreme. After the Big Bang, matter spread in a web-like pattern, with galaxies clustering along filaments and knots. The voids between them, those were expected to be modest, like bubbles in foam. But the Boötes void isn't a bubble, it's a cavern. If you placed Earth at its center, the night sky would be nearly black, with only faint smudges of distant galaxies breaking the darkness. No Milky Way, no Andromeda, just an endless void stretching farther than our minds can grasp. So how did this nothingness form? One theory suggests smaller voids merged over billions of years, like soap bubbles coalescing into one giant void. Another idea points to an ancient cosmic battle where dark energy and gravity waged war, with dark energy winning in certain regions, pushing matter away until almost nothing remained. There's even a fringe hypothesis that the void might be evidence of an advanced civilization, a Kardashev Type 3 empire that somehow harnessed the energy of entire galaxies, leaving behind a ghostly footprint. While that's unlikely, it underscores how baffling this phenomenon truly is. The eeriest part, the Boötes void, isn't alone. It's just the largest and most famous of many cosmic voids peppering the universe. Some, like the KBC void, are even bigger but less empty, while others challenge our models of how structure forms. These gaps force us to confront how little we understand about the universe's architecture. They're not flaws in the cosmos, they're clues hinting at forces or physics we've yet to discover. Standing on Earth, it's easy to feel like the universe is crowded with stars and galaxies. But the Boötes void reminds us that most of space isn't just empty, it's profoundly empty. A vacuum so extreme it redefines the word nothing. And somewhere in that void, the universe whispers a question we're still trying to answer. Why? Every beam of sunlight that warms your face is a time traveler. One that began its journey not just 8 minutes ago, but potentially tens of thousands of years in the past. Here's the twist. While sunlight reaches Earth in just over 8 minutes, the light you're seeing didn't start at the sun's surface. It was born deep in the core, where temperatures hit a staggering 15 million degrees Celsius and nuclear fusion turns hydrogen into helium. But escaping that dense, chaotic core, that's where things get slow. Picture a photon, a tiny packet of light, bursting into existence amid the sun's fusion frenzy. In open space, it would zip away at light speed, but the sun's core is so densely packed with atoms that the photon doesn't travel far before colliding with another particle. It's like trying to walk through a packed concert crowd, constantly bumped and redirected. Scientists call this the random walk, where the photon zigzags endlessly, taking baby steps toward the surface. Some estimates suggest this journey from core to surface could take up to 100,000 years. That means the sunlight you see today might have begun its odyssey back when early humans were just starting to migrate out of Africa. Once the photon finally escapes the sun's surface, though, it's smooth sailing. In just 8 minutes and 20 seconds, it races across 93 million miles of vacuum, untouched and undisturbed, until it lands on your skin or filters through leaves. The light hitting your eyes right now is a relic of two distinct eras, an ancient struggle through stellar plasma and a lightning-fast dash through the void of space. This delay isn't just a cosmic quirk, it's a lifeline. If the sun's core stopped producing energy this instant, we wouldn't know for millennia. The light already en route would keep arriving, and the sun's outer layers would continue radiating stored heat, buying Earth time before the true darkness set in. It's a chilling reminder that even our closest star operates on timescales far beyond human comprehension. So the next time you bask in sunlight, remember, you're not just feeling warmth. You're touching a whisper from the distant past, a message hurled across time and space, forged in the heart of a star that's been your silent, steadfast companion since before civilization began. Mercury isn't just the smallest planet in our solar system, it's also quietly caving in on itself. While Earth's tectonic plates shift and Mars's volcanoes sleep, Mercury is undergoing a cosmic contraction, shrinking like a raisin in the sun as its core cools. This slow-motion collapse has left the planet's surface scarred with towering cliffs, some stretching for hundreds of miles and climbing over a mile high. These aren't ordinary mountains, they're called lobate scarps, and they're the wrinkles of a world that's losing its inner fire. Here's why it's happening. Mercury has a massive iron core, making up nearly 85% of its radius. For comparison, Earth's core is only about half its radius. That dense core once burned hot, keeping the planet's outer layers flexible. But as the core cooled over billions of years, it solidified, contracting in the process. Imagine a grape left in the freezer. Its juicy interior turns to ice, shrinking and pulling the skin tight until it buckles. That's Mercury, but on a planetary scale. The crust, no longer supported by the cooling core, fractures and crumples, thrusting sections of the surface upward in sheer, jagged cliffs. The Messenger spacecraft, which orbited Mercury from 2011 to 2015, mapped these scarps in stunning detail. Some, like Enterprise routes, run almost 600 miles long, longer than the Grand Canyon, with slopes so steep they dwarf Earth's tallest rock faces. What's eerie is that these features are geologically young, suggesting Mercury is still shrinking today. Unlike Earth, where erosion smooths old scars, Mercury's lack of atmosphere and water means these cliffs stay razor-sharp, untouched by wind or rain for eons. Here's the twist: this shrinkage isn't just a quirk. it's rewriting our understanding of rocky planets. Scientists once thought small worlds like Mercury would cool too slowly to show such dramatic changes. Yet here it is, proving that even tiny planets can have seismic tantrums, and it raises a chilling question: could Earth someday shrink like Mercury? Probably not. Our planet's core stays hot thanks to radioactive decay and residual heat from its formation, while plate tectonics recycle the crust, preventing the kind of global wrinkling Mercury experiences. But Mercury's scars tell a deeper story. They're evidence of a planet caught between two fates, the fiery chaos of its birth and the icy stillness of its future. As the solar system's innermost world, it's bombarded by solar radiation, yet its heart grows colder by the day. Those cliffs aren't just geological features, they're the signatures of time itself, etched into rock as Mercury quietly folds inward, a silent reminder that even planets aren't immune to the slow march of change. Think outer space is a silent, endless void. Think again. Those iconic sci-fi scenes of total quiet, pure fiction. In reality, space is alive with eerie whispers, haunting hums, and even screaming plasma storms. We just can't hear them with human ears. Here's why. Sound as we know it needs air to travel, and space is a near-perfect vacuum. But swap sound waves for plasma waves, and suddenly the cosmos transforms into a symphony of invisible vibrations, detectable only with specialized instruments. Take Earth's own magnetosphere, for example. Our planet's magnetic field constantly battles the solar wind, a supersonic stream of charged particles from the sun. When these particles collide with Earth's magnetic shield, they don't just bounce off. They create ultra-low frequency waves that ripple through the plasma surrounding our planet. NASA Van Allen probes have captured these vibrations and translated them into audible frequencies, revealing something spine-tingling: Earth sings. Not with melodies, but with eerie chirps and whistles, like a celestial dolphin clicking in the dark. Scientists call these chorus waves. And they're not just artistic curiosities, they can actually accelerate particles to near light speeds, creating radiation belts that threaten satellites. But Earth isn't the only vocal planet. Jupiter's magnetic field is 20,000 times stronger than ours, turning its magnetosphere into a roaring concert hall. When NASA Juno spacecraft dipped close to the gas giant, its instruments picked up something straight out of a horror movie. A bone-rattling roar as charged particles screamed along magnetic field lines. Then there's Saturn, where the Cassini probe detected ghostly radio emissions from its aurora's patterns so rhythmic they've been dubbed the planet's dawn chorus. Even black holes join the choir. We've already talked about their sub-bass hums, but some supermassive black holes generate something far more dramatic: screaming jets of plasma traveling at nearly light speed. As these jets slam into interstellar gas, they create shockwaves that ripple for thousands of light years, vibrating the cosmos like a struck gong. The sound isn't sound in the traditional sense. It's pressure waves in superheated plasma, oscillating at frequencies millions of times lower than human hearing. But scale those waves up, and you get something closer to a continuous thunderclap, a cosmic drumroll marking the death of stars. So why does this matter? Because these sounds aren't just eerie background noise, they're clues. By listening to space, scientists can map magnetic fields, predict solar storms, and even probe the structure of distant galaxies. The universe isn't silent, it's shouting its secrets in a language of plasma and magnetism. We're only just learning to translate the chorus. Earth doesn't just have one moon, it's constantly playing gravitational host to a rotating cast of tiny, temporary companions. These fleeting cosmic hitchhikers, known as mini-moons, are typically small asteroids, some no bigger than a washing machine, momentarily snagged by Earth's gravity as they drift through the solar system. Unlike our permanent lunar neighbor, these visitors don't stick around for long. They might loop around us for a few months, even years, before breaking free and continuing their lonely journeys through space. The first confirmed mini-moon, a car-sized rock dubbed 2006 RH120, was spotted in 2006. It orbited Earth for about a year before slipping away, unnoticed by most of the planet. But in 2020, astronomers made an even more exciting catch. An object called 2020 CD3, roughly the size of a compact car, which circled Earth for nearly 3 years. What made this one special? Unlike typical asteroids, 2020 CD3 wasn't just passing by, it had been gently captured by Earth's gravity, becoming a bona fide, if temporary, second moon. Here's how it works. As asteroids journey around the Sun, some pass close enough to Earth that our planet's gravity briefly overpowers the Sun's pull. These objects don't enter stable orbits like the Moon. Instead, they follow chaotic, looping paths called temporary capture orbits. Picture a marble rolling around the rim of a bowl. It might circle a few times, but eventually it'll either fall in or roll away. That's the precarious dance of a mini-moon, forever on the edge of escape. What's wild is how common this might be. Simulations suggest Earth likely hosts at least one mini-moon 2 meters or larger at any given time, with countless smaller ones zipping around undetected. The challenge: spotting them. These objects are tiny, faint, and move unpredictably. Most are found by sheer luck, often by telescopes scanning for near-Earth asteroids. But new projects like the Vera C. Rubin Observatory in Chile promise to revolutionize mini-moon hunting. With its massive mirror and ultra-sensitive camera, it could start uncovering these elusive guests by the dozens. Why care about space rocks we can't even see without a telescope? Because mini-moons are time capsules. Some may be pristine fragments from the early solar system, untouched by the weathering that affects most asteroids. Others could even be human-made debris, old rocket boosters or satellites from decades past, finally looping back to our gravitational embrace. Studying them could reveal secrets about our cosmic neighborhood, or even offer practice for future asteroid mining missions. So while the Moon reigns supreme in our night sky, remember, Earth's gravitational reach is far busier than it seems. At this very moment, somewhere in the darkness, another unseen companion might be circling us, a silent guest in an endless celestial waltz. The Milky Way isn't the perfect spiral you see in textbooks. It's more like a vinyl record left out in the sun, warped and twisted at the edges. Recent observations reveal our galaxy's disk doesn't lie flat. Instead, it bends upward on one side and downward on the other, creating a subtle but unmistakable S-shape. This cosmic distortion spans hundreds of thousands of light years, with stars and gas clouds at the outer edges pulled into a gentle curve, as if the galaxy itself is tipping its hat to the universe. So what's bending our galactic neighborhood? The leading culprit is gravity's relentless tug of war. Smaller satellite galaxies, like the Large and Small Magellanic Clouds, orbit the Milky Way, their gravitational pull yanking on our galaxy's outer disk like invisible hands twisting a frisbee. Over billions of years, these interactions have left their mark, warping the thin plane of stars and dust into a shape that's more cosmic quass than perfect pancake. Computer simulations show the Magellanic Cloud's repeated passes could easily explain the Milky Way's wrinkles like ripples in a pond stirred by skipping stones. But here's the twist: the warp isn't static, it moves. Just as a spinning record wobbles, the Milky Way's distortion rotates around the galactic center, completing a full cycle every 600 to 700 million years. Stars near the warped edges don't just orbit the galaxy's core, they bob up and down through the disk like horses on a carousel, their paths tracing the rhythm of this vast, slow-motion dance. What's astonishing is how subtle this warp is from our vantage point. Nestled deep within the galactic disk, Earth's view is like an ant on a vinyl record too close to see the bend. Only by mapping the positions of thousands of distant stars using telescopes like Gaia have astronomers pieced together the true shape of our cosmic home. And it's not alone. About half of all spiral galaxies show similar warps, suggesting this isn't a flaw, it's a feature. A reminder that even galaxies aren't islands, but participants in a gravitational ballet, their forms sculpted by the invisible pull of their neighbors. So next time you picture the Milky Way, forget the textbook perfect spiral. Imagine instead a living, twisting structure, its edges swaying to the slow, silent music of the cosmos. While most planets in our solar system spin counterclockwise like a well-behaved cosmic top, Venus bucks the trend with a defiant clockwise rotation, so slow that a single Venusian day lasts longer than its entire year. This bizarre backward spin, called retrograde rotation, makes Venus the solar system's ultimate contrarian. But how did our so-called sister planet end up spinning in reverse? The answer might lie in ancient catastrophe or the relentless gravitational tug of war with the Sun. One leading theory points to violence in Venus's past, a colossal collision that literally knocked the planet sideways. Early in the solar system's chaotic youth, protoplanets and debris clashed constantly. A Mars-sized object slamming into Venus could have delivered enough force to flip its rotation entirely. Evidence for this comes from Uranus, which orbits on its side after a similar impact, proving such planetary rearrangements are possible. The impact scenario would also explain Venus's lack of moons. Any satellites it once had could have been obliterated or sent careening into space during the chaos. But there's another possibility. Tidal forces from the Sun may have gradually braked Venus's spin until it reversed. Venus orbits closer to the Sun than Earth, where solar gravity exerts an especially powerful influence. Over billions of years, the Sun's tidal pull combined with friction from Venus's thick, sluggish atmosphere could have slowed the planet's original rotation to a standstill before nudging it backward. Picture pushing a child on a swing. If you time your pushes just right, you can gradually reverse their motion. The Sun might have done something similar to Venus, using gravity as its cosmic hands. Here's where it gets even stranger. Venus's retrograde spin isn't its only oddity. Its day-night cycle is equally surreal. The planet takes 243 Earth days to complete one rotation, but only 225 days to orbit the Sun. This means if you stood on Venus's scorching surface, assuming you could survive the 900-degree heat and crushing atmospheric pressure, the Sun would rise in the west, set in the east, and then not rise again for nearly 4 Earth months. Theories aside, Venus's backward dance remains one of planetary science's great puzzles. Every probe we've sent from the Soviet Venera landers to NASA's a Magellan orbiter has uncovered new mysteries without fully settling the debate. Future missions, like the upcoming Veritas orbiter, might finally decode the planet's turbulent past by mapping its gravity field and surface features in unprecedented detail. Whatever the cause, Venus's rebellious spin is a reminder that the universe loves exceptions to the rules. Even in something as fundamental as a planet's rotation, nature finds ways to surprise us, turning what should be orderly into something wonderfully strange. Deep in the void between stars, where temperatures hover just above absolute zero, a vast cloud of gas drifts through space, and it smells surprisingly like dessert. Astronomers analyzing the Sagittarius B2 molecular cloud, a sprawling stellar nursery 25,000 light-years from Earth, made an unexpected discovery. This cosmic nursery is laced with ethyl formate, the same molecule that gives raspberries their sweet, fruity aroma. That's right, if you could take a deep breath in the heart of our galaxy and survive the lack of oxygen and freezing vacuum, the universe might just remind you of a cosmic bakery. But ethyl formate isn't floating alone in this interstellar pantry. Over 200 other complex molecules have been detected in similar gas clouds, from ethanol, the same alcohol found in cocktails, to glycolaldehyde, a simple sugar that's a building block for RNA. These discoveries flip the script on deep space. Instead of a barren wasteland, it's more like a sprawling chemical kitchen, quietly simmering the ingredients for life. How does this cosmic cooking work? Imagine a vast, diffuse cloud of gas and dust, so thin that a teaspoon of it would contain only a few thousand atoms. Over millions of years, gravity nudges these particles together, and on the surface of dust grains, atoms link up to form molecules. Radiation from nearby stars provides the energy to forge even more complex compounds like ethyl formate. It's not quite a raspberry factory, but it's proof that the universe has a flair for organic chemistry long before planets or life enter the picture. Now, before you picture a galaxy that literally smells like jam, there's a catch. Space might contain these aromatic molecules, but without an atmosphere to carry scent, you'd never actually smell them. Ethyl formate's raspberry-like fragrance only emerges when it's dissolved in a liquid or suspended in air, conditions that don't exist in the vacuum between stars. But that doesn't make the discovery any less tantalizing. These molecules are the precursors to far more complex organic materials, the kind that could seed planets with the building blocks of life. The real magic lies in what this means for the search for life beyond Earth. If the ingredients for flavors, fragrances, and even sugars are already floating between the stars, then the universe might be pre-stocked with the raw materials for biology. It's as if the cosmos set the table long before the first microbes arrived. So while you won't find interstellar raspberry pies anytime soon, you can marvel at a universe that's not just vast and mysterious, but unexpectedly, deliciously familiar. For over 300 years, Jupiter's Great Red Spot has been the solar system's most iconic storm, a swirling crimson maelstrom wider than Earth itself, raging with winds that scream at 430 miles per hour. But this legendary tempest is fading before our eyes, shrinking faster than scientists ever predicted. What was once a behemoth spanning 25,000 miles in the 1800s could now barely swallow our planet whole, measuring just 10,000 miles across. Even more alarming, the storm isn't just getting smaller. It's changing shape, morphing from a proud oval into a squashed circle like a deflating balloon. The mystery isn't just why the Great Red Spot is shrinking, but how it existed for centuries in the first place. Earth's hurricanes fizzle out in days when they hit land or cold water, yet Jupiter's mega storm has persisted since astronomers first spotted it in the 1600s, possibly even longer. The secret lies in Jupiter's lack of a solid surface. Without continents or oceans to sap its energy, the storm feeds off the planet's chaotic atmospheric currents, drawing heat from Jupiter's scorching interior. It's a self-sustaining vortex, spinning like a cosmic top in a sea of hydrogen and helium. Yet even immortal storms have limits. Recent images from the Hubble Space Telescope reveal the spot isn't just contracting, it's unraveling at the edges, with crimson flakes peeling away like paint from an old barn. Some researchers blame turbulent jet streams chipping at its periphery, while others suspect changes in Jupiter's internal heat distribution are starving the storm. There's even a theory that the spot is somehow splitting, with smaller vortices occasionally breaking off and dissipating into the surrounding clouds. So how much time does the Great Red Spot have left? Predictions vary wildly. Some models suggest it could vanish within our lifetimes, collapsing into a harmless swirl by 2040. Others argue it might stabilize at a smaller size, becoming a shadow of its former self but never fully disappearing. There's also a spine-tingling third option. The spot might not be dying at all but transforming. In 2019, astronomers spotted strange blade-like structures spinning off the storm, possible signs of rebirth, not decay. Whatever its fate, the Great Red Spot's decline forces us to confront a humbling truth. Even the most permanent-seeming features of our solar system are fleeting on cosmic scales. Whether it sputters out in decades or lingers for centuries, this ancient storm's final act will rewrite textbooks and remind us that the universe reserves the right to change the rules without warning. Somewhere in the constellation Cancer, a planet orbits so close to its star that a single year lasts just 18 hours, and its surface might be the ultimate cosmic jewel. Meet 55 Cancri, a world where carbon isn't just an element, it's the foundation of an entire planet, crushed under such extreme conditions that scientists believe much of it has crystallized into diamond. Imagine a landscape where mountains aren't made of rock, but of glittering gemstones and rivers of molten graphite carve valleys under a perpetually scorching sky. Discovered in 2004, this super-Earth is about twice our planet's size but nearly 8 times as massive, with a density that hints at something extraordinary beneath its broiling exterior. Orbiting a sun-like star 40 light-years away, 55 Cancri's carbon-rich composition comes from its home system's unusual chemistry. Most planetary systems, like ours, form from nebulae rich in oxygen and silicon ingredients for rocky worlds. But this star system had far more carbon than oxygen, creating the perfect recipe for diamonds on a planetary scale. The physics behind this glittering metamorphosis is staggering. Under normal conditions, carbon forms graphite, the stuff in pencil lead. But when subjected to crushing pressures hundreds of thousands of times greater than Earth's surface, carbon atoms rearrange into the tetrahedral lattice of diamond. On 55 Cancri, the planet's immense gravity and searing temperatures reaching nearly 2,700 degrees Celsius on its day side could have transformed up to a third of its mass into this crystalline form. Some models suggest its interior might harbor a diamond layer hundreds of miles thick, a sparkling mantle beneath a thin crust of graphite and vaporized hydrocarbons. But don't picture a perfectly polished cosmic engagement ring. This world is anything but serene. Tidal forces from its star have likely locked one side in permanent daylight, where temperatures melt rock into lava oceans while the night side simmers in perpetual twilight. The diamond-rich interior might ooze upward through volcanic fissures, creating glittering geodes the size of continents. And because carbon conducts heat so efficiently, the planet could sport bizarre weather patterns, jet streams of superheated carbon vapor racing across its surface, or diamond rain condensing in its upper atmosphere before plunging back into the depths. The wildest part, 55 Cancri might not be alone. Carbon-rich planets could be common around stars with similar chemistry, meaning the universe might be littered with diamond worlds, each one a testament to how extreme conditions can turn familiar elements into something unimaginably alien. While we'll never mine these distant gems, a round trip would take centuries with current technology. Their existence reshapes our understanding of planetary diversity. After all, if a world can be made of diamond, what other impossible-sounding wonders might be waiting in the cosmos? We all learn that light travels at a constant speed, 300,000 kilometers per second in a vacuum, the universe's ultimate speed limit. But here's the twist: light can slow down, and under the right conditions, scientists have even brought it to a near standstill. This isn't some loophole in physics. It's a fundamental property of light's interaction with matter, and it reveals how reality bends the rules in ways that defy intuition. Take something as simple as a glass of water. When light enters water or glass or diamond, it doesn't barrel through at full cosmic speed. Instead, it slows, dragged down by interactions with the atoms in its path. In water, light travels about 25% slower than in a vacuum. Through diamond, that speed plummets to less than half. The photons aren't losing energy, they're being absorbed and re-emitted by atoms in a frenzied subatomic relay race, creating a net slowdown that makes light appear to dawdle. But the real magic happens in the lab. In 1999, physicists at Harvard performed what seemed like pure sorcery. They brought light to a crawl, reducing its speed to a mere 17 meters per second, about the pace of a bicycle. They didn't defy Einstein, they outsmarted the problem. By supercooling a cloud of sodium atoms to near absolute zero and hitting them with precisely tuned lasers, they created a state of matter where photons became entangled with the atoms, trudging through the cloud like a crowd moving through molasses. Then came the real shocker. In 2013, researchers in Germany stopped light entirely for a full minute. They used a crystal doped with rare earth elements, freezing light's information in place by transferring it to the atomic spins of the crystal structure. The photons effectively vanished, their essence stored in the material like a cosmic pause button before being re-released as light again. This isn't just a parlor trick, it's the foundation for quantum memory, a critical step toward unhackable communication and light-based computing. So why doesn't this violate relativity? Because the speed of light in a vacuum, the c in Einstein's famous equation, remains unbreakable. Light's slowdown in matter is a collective illusion, a dance of absorption and re-emission that creates lag without breaking the rules. But these experiments expose a deeper truth. Light isn't just a beam, it's a conversation between energy and matter, one we're only beginning to decode. And somewhere between the frozen pauses and diamond-dragged photons, the universe whispers that even its most rigid laws have room for wonder. Saturn's dazzling rings might be the solar system's ultimate illusion, a breathtaking spectacle that's far younger than the planet itself and already on borrowed time. For centuries, we assumed these icy bands were as ancient as Saturn, forming alongside the gas giant over 4 billion years ago. But data from NASA Cassini spacecraft shattered that assumption, revealing the rings might be a mere cosmic blink in age, possibly just 100 million years old. That means when dinosaurs ruled Earth, Saturn might have been naked. How do we know? Cassini's final, fateful plunge into Saturn in 2017 provided critical clues. As the probe skimmed the inner edge of the rings, it measured their mass with unprecedented precision. And that's where things got interesting. The rings turned out to be startlingly light, just 40% as massive as one of Saturn's mid-sized moons. This featherweight profile points to a youthful origin. Over billions of years, the rings should have accumulated more dust and debris from meteoroid impacts, growing heavier and darker. Yet they remain remarkably pristine, their ice glittering like fresh snowfall. But the real bombshell came from studying the ring's erosion. Saturn's gravity is relentless, pulling icy particles inward in a slow-motion downpour. Dubbed ring rain, this process sends thousands of kilograms of material tumbling into the planet's atmosphere every second. Add micrometeoroid impacts and solar radiation blasting particles away, and the math becomes grim. At this rate, the rings could vanish entirely within another 300 million years. Imagine a celestial hourglass with Saturn's iconic features slipping away grain by grain. So where did the rings come from if they're not primordial? The leading theory involves a brutal celestial breakup, perhaps a small, icy moon that wandered too close and was shredded by Saturn's gravity, or a comet that strayed into the gas giant's grasp and shattered. The debris from this cataclysm would have spread into a disk, gradually organizing into the structured rings we see today. It's a reminder that even the most serene-looking corners of the cosmos can hide violent past. What's haunting is the timing. In a universe where most wonders operate on billion-year timescales, Saturn's rings are fleeting, a temporary marvel we're lucky to witness. By the time Earth's continents merge into the next supercontinent, Saturn's crowning glory could be gone, leaving future astronomers to puzzle over ancient spacecraft images of a jewel that once was. For now, though, those icy bands remain a shimmering reminder that beauty in the cosmos is often ephemeral, and that we live in a privileged sliver of time when the solar system wears its finest jewelry. What if everything you see, touch, and experience, every star, every atom, even your own thoughts, is just an illusion, a shadow cast by information encoded on some distant two-dimensional surface? This isn't the plot of a sci-fi movie. It's the holographic principle, one of the most radical ideas in modern physics. At its core, the theory suggests our three-dimensional universe might be nothing more than a projection, like a cosmic hologram, with all its complexity emerging from a flat, boundary layer we can't perceive. The roots of this mind-bending concept trace back to black holes. In the 1970s, physicist Jacob Bekenstein discovered something astonishing. The entropy, or information content, of a black hole isn't proportional to its volume as you'd expect, but to its surface area. Later, Stephen Hawking confirmed that black holes emit radiation and slowly evaporate, raising a terrifying question. What happens to all the information swallowed by a black hole if it eventually disappears? The answer, proposed by theorists like Leonard Susskind and Gerard T. Hooft, was as elegant as it was bizarre. The information isn't lost, it's smeared across the black hole's event horizon like a celestial hard drive, preserving it in 2 dimensions. From there, the idea snowballed. If black holes encode 3D information on 2D surfaces, could the entire universe work the same way? Imagine the cosmos as a vast movie screen, with every event, every supernova, every falling leaf playing out as ripples on its surface. What we perceive as depth, time, and motion might just be the universe reading that flat data and rendering it in 3 dimensions for our benefit. Support for this theory comes from unexpected places. In 1993, Dutch physicist Gerard T. Hooft and American Leonard Susskind formalized the holographic principle, arguing that it could resolve paradoxes in quantum gravity. Then, in 1997, Argentine physicist Juan Maldacena discovered a concrete mathematical link between a 5-dimensional anti-de Sitter space, a theoretical model of the universe, and a 4-dimensional conformal field theory, its lower-dimensional shadow. This AD/S/CFT correspondence became the first rigorous evidence that a higher-dimensional reality could emerge from a lower-dimensional one. But how could this possibly work in our universe? Think of a credit card hologram, that shiny sticker where a 3D image seems to float above the surface. The sticker itself is flat, but the way light scatters off its microscopic grooves creates the illusion of depth. The holographic principle suggests reality might operate similarly, with quantum bits on some distant boundary acting like those grooves, projecting the rich tapestry of our 3D world. Not everyone's convinced, of course. Critics point out that Maldacena's model describes a universe with negative curvature, a far cry from our flat, expanding cosmos. And translating the math to observable physics remains a colossal challenge. But if the holographic principle holds, it would rewrite our understanding of existence. Space itself would be emergent, not fundamental, and the universe's true source code would reside on a hidden surface we'll likely never see. Here's the wildest implication. If the universe is a hologram, then at some level you and I are too. Our sense of solidity, of separateness, even our perception of time, might just be the universe's way of interpreting data too vast and strange for our minds to grasp directly. The next time you hold an object, look at your hands, or gaze at the stars, remember, you might not be seeing reality as it truly is, but only the breathtaking projection of something far simpler, playing out on the edges of the unknown. Mars doesn't just have dust storms, it has planet-sized tempests that swallow the entire world in a suffocating haze for months. Picture a blizzard, but instead of snow, imagine trillions of razor-fine dust particles churned into the sky, blotting out the sun until the entire landscape drowns in perpetual twilight. These aren't localized sandstorms like Earth's desert gales. They're global apocalypses, turning Mars from a rusty desert into a featureless orange fog so thick it obscures every mountain, canyon, and rover from orbit. The most recent monster storm hit in 2018, engulfing Mars so completely that NASA Opportunity rover, a resilient machine that had survived 14 years of harsh conditions, finally met its end. Solar panels caked in dust couldn't recharge its batteries, and after 1,500 attempts to wake it, engineers declared the mission over. But the storm's scale was even more staggering than its casualty. It didn't start as a global event. It began as a small dust cloud near the equator, then metastasized across the planet in weeks, driven by winds that whipped dust particles high into the thin atmosphere. Unlike Earth storms, which fizzle when they hit oceans or mountains, Mars's lack of geographic barriers lets tempests spread unchecked, feeding on sunlight that heats airborne dust and fuels even fiercer winds. For future astronauts, these storms pose more than just visibility issues. The dust isn't harmless powder, it's electrostatically charged, clinging to spacesuits, solar panels, and machinery like cosmic glitter gone rogue. Even sealed habitats wouldn't be immune. During a global storm, dust could clog air filtration systems, coat solar arrays until power production plummets, and potentially even seep into mechanical joints, wearing down equipment faster than engineers anticipated. Then there's the psychological toll. Imagine being stranded inside for months, watching the sun dim to a faint orange smudge while howling winds shake your habitat's walls. Yet there's a strange beauty to these storms. Without rain or oceans to wash the sky clean, Martian dust can linger for months, painting sunrises and sunsets in surreal shades of blue. The thinner atmosphere scatters light differently than Earth's, creating a phenomenon called blue haze, where the sky takes on an eerie cerulean tint at dusk and dawn. For all their deadliness, these storms also sculpt Mars's surface, redistributing dust in patterns that reveal hidden wind currents and even temporarily darkening regions as vast as continents. The bigger mystery: why some years produce planet-engulfing monsters while others see only regional squalls. Some scientists suspect orbital eccentricity plays a role. Mars's elliptical orbit means sunlight intensity varies by 30% throughout its year, possibly triggering superstorms when conditions align. Others point to dust reservoirs, giant dune fields that act as fuel depots for atmospheric chaos. Solving this puzzle isn't just academic, it's survival. Before humans can colonize Mars, we'll need storm prediction systems as reliable as Earth's hurricane trackers, giving settlers days or weeks to batten down the hatches. So while Mars's rust-colored plains might seem tranquil from afar, they hide a world capable of fury on a scale Earth hasn't seen in millennia. These storms aren't just weather, they're reminders that even our closest planetary neighbor operates by rules we're only beginning to decode. And for the first pioneers who brave its surface, surviving Mars won't just mean mastering technology, it'll mean weathering literal planetary tantrums that redefine what it means to endure. At first glance, the idea of a star older than the universe sounds like a cosmic paradox, a glitch in the matrix of reality. Yet nestled in the constellation Libra, a faint yellow star dubbed the Methuselah star, or HD 140283, seems to defy the laws of physics. Based on initial measurements, this ancient relic appeared to be 14.5 billion years old, a staggering 1 billion years older than the universe itself. That's like finding a fossilized dinosaur bone dated to a time before Earth even existed. So how does a star outpace the cosmos in age? The answer lies in the delicate, often contentious science of stellar archaeology. Pinpointing a star's age isn't as simple as reading a cosmic birth certificate. Astronomers rely on clues like chemical composition, brightness, and motion to piece together its history. The Methuselah star is a subgiant, transitioning from burning hydrogen to helium, a phase that betrays its advanced years. But the real smoking gun is its near-total lack of heavy elements. Early in the universe's history, before generations of stars had forged metals in their cores and scattered them through supernova, stars were made almost entirely of hydrogen and helium. Methuselah's pristine composition suggests it's a first-generation star, a rare survivor from the dawn of time. The controversy erupted when early calculations, factoring in the star's distance, luminosity, and elemental makeup, suggested an age that overshot the universe's known lifespan. Skeptics pounced. Either the star's age was wrong, or our understanding of cosmic chronology was missing something monumental. Further scrutiny revealed a cascade of variables that could skew the math. For instance, the star's oxygen-to-iron ratio, critical for age estimates, was initially miscalculated. Revised data from the Hubble Space Telescope in 2014 adjusted Methuselah's age downward, but only slightly, to 14.27 billion years, still uncomfortably close to the universe's 13.8 billion year benchmark. The real breakthrough came when scientists incorporated the universe's accelerating expansion into their models. Dark energy's push stretches space itself, meaning distances, and thus the time light takes to reach us aren't static. Adjusting for this cosmic stretching, combined with tighter measurements of the star's parallax, brought Methuselah's age into alignment at 13.7 billion years, just under the universe's age. Crisis averted, but not without leaving a trail of existential questions. What makes Methuselah so fascinating isn't just the margin of error drama. It's a living relic from an era when the first starlight pierced the cosmic dark. Its existence hints at gaps in our knowledge about the early universe, from the exact moment stars first ignited to the subtle dance of dark energy over time. For astronomers, it's both a benchmark and a provocation, a reminder that even the most steadfast laws of physics sometimes flirt with the impossible. So while Methuselah may no longer break the universe's age limit, it still holds a record, the closest we've ever come to touching the very edge of time itself. Some of the universe's greatest mysteries aren't blazing stars or swirling nebulae. They're the cosmic graveyards of red and dead galaxies, colossal islands of stars that burned bright before shutting down billions of years ago. Unlike our Milky Way, which still births new stars in shimmering stellar nurseries, these galaxies are frozen in time, their gas reservoirs exhausted or stolen, leaving behind only aging red giants and the faint glow of fading embers. They're the celestial equivalent of ghost towns, their streets once bustling with stellar life now silent and unchanging. Take Messier 87, the monstrous galaxy at the heart of the Virgo cluster. While it's famous for harboring a supermassive black hole, it's also a prime example of a red and dead giant. Its golden hue isn't just aesthetic, it's a telltale sign of senescence. Young blue stars have short, fiery lives and die quickly, while older red stars burn slowly for eons. When a galaxy stops making new stars, the blue ones vanish first, leaving behind a reddish population that dominates the light spectrum. But how does an entire galaxy just stop? The leading theory involves a brutal cosmic eviction. Many red and dead galaxies live in dense clusters where gravitational interactions strip away their gas, the raw material for new stars. Picture a galaxy sailing through a cluster's hot, thin intergalactic medium. The pressure alone can rip away its gas like wind tearing leaves from a tree. Other times, supermassive black holes at galactic centers go berserk, spewing jets of energy so powerful they heat and expel gas far beyond the galaxy's reach. Without fresh fuel, star formation grinds to a halt, and the galaxy settles into a quiet, crimson retirement. But here's the spine-tingling part. Some of these galaxies died when the universe was just a fraction of its current age. The James Webb Space Telescope recently spotted galaxies that had already gone red and dead when the cosmos was only 3 billion years old, a cosmic toddler by universal standards. That's like finding a fossilized city buried beneath a playground. How could entire galaxies burn out so quickly? One possibility is that they formed stars at a breakneck pace early on, exhausting their gas supplies in a frenzied burst of creation before collapsing into stagnation. The eeriest detail, our Milky Way is on a collision course with Andromeda, and their eventual merger could trigger a similar fate. As the two galaxies smash together, the chaos might funnel too much gas into their central black holes, igniting violent outbursts that sterilize the remaining gas. Billions of years later, the combined Milkomda galaxy could join the ranks of the red and dead, its spiral arms fading into a featureless red haze. Yet even in their twilight, these galaxies aren't truly lifeless. Their stars still orbit, their black holes still lurk, and their planets, if any survive, might harbor civilizations watching their skies darken forever. They're a preview of the universe's far future when star formation flickers out and the cosmos settles into a long, quiet night. For now, they stand as silent sentinels, reminding us that even galaxies have lifetimes and that the universe's most enduring structures are often those that have already run out of time. Most planets spin like tops as they orbit the Sun, with their poles pointing roughly upward relative to their orbital plane. But Uranus, it doesn't spin, it rolls. Tilted a jaw-dropping 98 degrees, this ice giant doesn't just lean slightly like Earth's 23-degree tilt. It's practically doing cosmic cartwheels, orbiting the Sun on its side like a wayward bowling ball. This extreme posture gives Uranus the most bizarre seasons in the solar system, stretching decades of unending sunlight or pitch-black darkness over entire hemispheres. Imagine standing near Uranus's north pole during its summer solstice. The sun wouldn't rise or set, it would spiral slowly overhead in a tight circle for 21 straight Earth years, barely dipping below the horizon. Then, as Uranus completes its 84-year orbit, that same pole would plunge into a winter so long and dark it makes Arctic nights look fleeting. For creatures used to Earth's relatively gentle seasons, this would be incomprehensible. Summers where the sun never leaves the sky, winters where it never appears, and springs where the star rises and sets sideways, tracing bizarre corkscrew paths across the heavens. How did Uranus end up like this? The leading theory involves a violent collision. Not just a glancing blow, but a head-on smash with an Earth-sized object early in the solar system's history. The impact likely knocked Uranus off its original axis, leaving it spinning like a toppled gyroscope. Unlike other planets which have stabilized over billions of years, Uranus never fully recovered, forever locked in its sideways shuffle. Some simulations suggest multiple impacts could have caused this, or even gravitational tugs from other giants like Jupiter, but the collision theory remains the most compelling. The tilt doesn't just affect sunlight, it warps Uranus's entire magnetic field. Unlike Earth's relatively aligned magnetic poles, Uranus's field is off-kilter, skewed by nearly 60 degrees from its already extreme rotational axis. This creates a magnetosphere that wobbles chaotically as the planet spins, opening and closing like a lopsided umbrella. Solar wind particles get funneled along these unpredictable paths, potentially creating auroras that zigzag across the atmosphere in ways no other planet experiences. Even Uranus's weather is tilted literally. When Voyager 2 flew by in 1986, it saw a bland, featureless blue ball. But decades later, ground-based telescopes and Hubble revealed raging storms and bright cloud bands, likely because Uranus had reached a point in its orbit where the sun finally struck areas that had been in shadow for years. The sudden warmth might have stirred up winds exceeding 500 miles per hour, proving that even a seemingly quiet ice giant has atmospheric drama when the seasons shift. What's eerie is how Uranus's moons and rings obey this sideways logic too. They orbit around its equator, meaning they circle the planet like the rings of a bullseye, perpendicular to the solar system's plane. From Earth, we sometimes see these rings edge on, a razor-thin line, and other times face on, like a giant target painted around the planet. It's a stark reminder that Uranus doesn't just defy norms, it rewrites them, forcing every part of its system to conform to its topsy-turvy reality. The deeper mystery, Uranus isn't alone. Venus also spins oddly, though in the opposite direction. But Uranus stands apart with its extreme tilt, a cosmic oddball that challenges our assumptions about how planets form and evolve. Future missions like NASA's proposed Uranus orbiter could unravel more secrets, perhaps even revealing whether the planet's interior, with its hypothesized slushy water ammonia ocean, plays a role in maintaining this bizarre orientation. For now, Uranus remains a puzzle, a world where the rules of day and night, seasons and storms, all bend to the whims of a single ancient cataclysm. It's a reminder that the solar system has no obligation to make sense to us, and that even the quietest-looking worlds can harbor the strangest stories. If two coins could somehow remain perfectly linked no matter how far apart they traveled, flipping one instantly determining the fate of the other, you'd have a crude analogy for quantum entanglement, one of the most baffling phenomena in the universe. At the subatomic level, particles like electrons or photons can become entangled, their properties intertwined in such a way that measuring one instantly influences its partner, even if they're on opposite sides of the galaxy. This isn't just theoretical. Experiments have confirmed that entangled particles coordinate faster than light could travel between them, as if space and time don't apply to their connection. Take the famous Einstein-Podolsky-Rosen-Eppler paradox, dreamed up in 1935 to challenge quantum theory. Einstein called this spooky action at a distance, refusing to believe particles could communicate instantaneously. He assumed some hidden variables, unknown properties, must predetermine their states. But in the 1980s, physicist Elaine Aspect conducted groundbreaking experiments that shattered Einstein's hopes. By measuring entangled photons at distances that light couldn't cross in time, he proved their coordination was real and instantaneous. The implications were staggering. Either information was traveling faster than light, breaking relativity, or the particles existed in a state of pure potentiality until observed, with no fixed reality until measured. Here's where it gets even wilder. Entanglement isn't just a lab curiosity, it's the foundation of quantum teleportation. Not the sci-fi kind where objects vanish and reappear, but the transfer of quantum states between particles. In 1997, scientists teleported the quantum state of a photon across a lab. By entangling two photons, then measuring one alongside a third target photon, they could destroy the target's original state while recreating it perfectly on the distant entangled partner. The original photon wasn't physically moved. Its quantum essence was transmitted through the entanglement link, effectively teleporting its information. This isn't magic. It's the bizarre logic of quantum mechanics, where particles don't play by classical rules. Imagine two dice that always land on matching numbers, even if rolled in separate galaxies. Entanglement suggests the universe at its smallest scales operates as a deeply interconnected web, where separation is an illusion and particles remain bound by invisible threads. Yet there's a catch. This teleportation can't send messages faster than light. While the entanglement link is instantaneous, decoding the teleported state requires classical communication limited by light speed. It's like receiving a locked box and a key shipped separately. The box arrives instantly, but you still need to wait for the mailman to deliver the key to open it. What's truly mind-bending is how entanglement challenges our notion of locality, the idea that objects are only influenced by their immediate surroundings. Quantum mechanics paints a universe where particles share a hidden unity, as if the cosmos itself is stitched together by threads we're only beginning to glimpse. For all its strangeness, this phenomenon isn't just abstract math. It's the backbone of emerging technologies like quantum cryptography and computing, where entangled particles could revolutionize data security and processing. So while we're not teleporting people anytime soon, entanglement reveals a universe far more interconnected than Einstein ever imagined. One where particles whisper to each other across the void, defying distance and redefining what it means to be separate. The moon isn't the silent, lifeless world it appears to be. It rattles and shakes with its own version of earthquakes, known as moonquakes. Unlike Earth's tectonic tremors, these lunar seismic events are triggered by entirely different forces, and some can last for hours, reverberating through the moon's brittle crust like a struck bell. The absence of water and atmosphere on the moon means there's nothing to dampen these vibrations, allowing them to persist far longer than any quake on Earth ever could. One of the most common causes of moonquakes is Earth's relentless gravitational pull. Just as the moon's gravity tugs on our oceans to create tides, Earth's gravity stretches and compresses the moon's rigid interior. This tidal flexing generates deep, slow-rolling quakes that originate dozens of miles beneath the surface. The Apollo missions left behind seismometers that recorded thousands of these events, revealing a surprising pattern. Moonquakes often synchronize with the moon's closest and farthest points in its elliptical orbit when Earth's tidal grip is strongest. Then there are the more violent moonquakes caused by meteor impacts. Without an atmosphere to burn up incoming debris, the moon's surface is constantly bombarded by space rocks, some as small as pebbles, others as large as trucks. These impacts send shockwaves rippling through the lunar crust, triggering seismic waves that can travel hundreds of miles. The most dramatic recorded example happened in 1972, when a boulder-sized meteor slammed into the moon's surface, producing a moonquake so powerful it registered for over 4 hours. On Earth, an earthquake of that magnitude would have flattened cities, but the moon's dry, rigid structure lacks the dampening effects of water or sediment, allowing the vibrations to echo endlessly. But the strangest moonquakes of all might be the shallow, high-frequency tremors detected near the lunar surface. Unlike tidal or impact quakes, these events remain poorly understood. Some scientists speculate they could be caused by thermal stress, the extreme temperature swings between lunar day and night, which can reach over 500 degrees Fahrenheit, causing the crust to expand and crack. Others suggest they might be linked to ancient fault lines, remnants of a time when the moon was still geologically active. The moon's seismic activity isn't just a curiosity, it's a crucial puzzle piece for future lunar exploration. Understanding where and why moonquakes happen could determine where we build permanent bases, ensuring structures are safe from unstable terrain. It also raises a haunting possibility. If the moon isn't entirely geologically dead, could there still be pockets of molten rock deep below its surface? Every tremor is a clue, a hidden message in the vibrations of a world we've only just begun to understand. So the next time you look up at the moon, remember, beneath that serene, cratered face, it's still stirring, still shaking, a silent world with a restless soul. Somewhere in the depths of the Milky Way, about 26,000 light-years from Earth, floats a cosmic pub unlike any other. A vast interstellar cloud packed with enough alcohol to fuel every bar on the planet for billions of years. Known as Sagittarius B2, this gargantuan star-forming region doesn't just contain a few stray molecules of ethanol. It's a swirling reservoir of billions upon billions of liters of the stuff, mixed with other organic compounds that make it smell like a celestial distillery gone rogue. This isn't just a fun fact for trivia night. It's a window into the universe's surprising knack for organic chemistry. Spanning over 150 light-years, Sagittarius B2 is a molecular cloud so dense and rich in complex molecules that scientists have dubbed it a giant interstellar pantry. Alongside ethanol, it's laced with ethyl formate, which gives raspberries their scent, acetic acid the pungent component of vinegar, and even glycolaldehyde, a simple sugar that's a building block for RNA. If you could take a deep breath in this cloud, assuming you survived the lack of oxygen, and near absolute zero temperatures, the aroma might remind you of a bizarre cocktail mixing fruity sweetness with sharp, sour notes. But how does a cloud in space end up smelling like a cocktail lounge? The answer lies in the chaotic dance of chemistry happening on the surfaces of dust grains. In the frigid vacuum of space, individual atoms and simple molecules like carbon monoxide and hydrogen stick to microscopic specks of silicate or carbon dust. Over millions of years, radiation from nearby stars provides just enough energy to nudge these atoms into forming more complex compounds. Ethanol, for instance, forms when hydrogen atoms bond with carbon and oxygen in precise arrangements, a process that, against all odds, happens efficiently in the freezing darkness of interstellar space. Before you picture a universe-wide happy hour, though, there's a catch. Sagittarius B2's alcohol isn't floating around in liquid form, ready to be poured into a glass. It's dispersed as a gas, with molecules so sparse that you'd need to gather an unimaginably large volume to fill even a single shot glass. And even if you could bottle it, this cosmic hooch wouldn't be safe to drink. It's mixed with toxic compounds like formaldehyde and hydrogen cyanide, turning the fantasy of interstellar breweries into a decidedly lethal proposition. What makes Sagittarius B2 truly remarkable isn't just its intoxicating contents, but what it tells us about the origins of life's ingredients. Clouds like this are stellar nurseries where new stars and planets coalesce from gas and dust. The organic molecules they contain, alcohols, sugars, and acids, can hitch a ride on comets or asteroids, eventually landing on young worlds like Earth billions of years ago. Some scientists speculate that the building blocks of life might have arrived here pre-packaged, courtesy of molecular clouds not so different from this one. So while we won't be opening a space-age distillery anytime soon, Sagittarius B2 offers a heady reminder: the universe isn't just a vast, empty void. It's a chemist's playground, simmering with the raw materials for flavors, fragrances, and perhaps even life itself, all swirling together in a cosmic cocktail mixer older than the solar system. Our sun may seem like a permanent fixture in the sky, a reliable golden ball that rises and sets with clockwork precision, but in cosmic terms, it's just middle-aged. 5 billion years from now, this familiar star will enter its retirement years with a dramatic transformation that will rewrite the solar system as we know it. As the sun exhausts the hydrogen fuel in its core, it will swell into a red giant, expanding to over 200 times its current size and swallowing Mercury, Venus, and likely Earth in a fiery farewell. The process begins when the sun's core can no longer sustain nuclear fusion. With hydrogen depleted, gravity will cause the core to contract, heating up until it reaches temperatures hot enough to ignite helium fusion. This new energy source will push the sun's outer layers outward with incredible force, turning it from a yellow dwarf into a bloated, orange-red behemoth. The sun's surface will cool slightly, but its sheer size will make it thousands of times brighter than it is today, bathing what remains of the inner solar system in intense, scorching radiation. Mercury, the closest planet, won't stand a chance. As the sun's outer layers expand, they'll engulf the tiny world, dragging it into a spiraling death plunge. Venus, despite its thick atmosphere, will meet the same fate, its rocky surface vaporized long before the sun's photosphere reaches it. Earth sits right on the edge. Whether it's consumed or merely scorched depends on subtle factors like mass loss from solar winds and tidal interactions. Some models suggest the sun's expansion might push Earth into a wider orbit just out of reach. But even if our planet avoids being swallowed, it won't be spared. The oceans will boil away, the atmosphere will be stripped by stellar winds, and the surface will melt into a global magma ocean. The charred remains of continents will drift across this molten hellscape until the sun's outer layers finally recede. This apocalyptic future isn't just theoretical, we've seen it happen elsewhere in the galaxy. Stars like Kepler-56 and WASP-12 are already in their red giant phases, their planets withering under the onslaught. In some cases, the expansion is so violent that planets are torn apart before being fully engulfed, their debris forming glowing rings around their dying stars. Others, like the doomed world Kepler-91b, are being slowly eaten as their atmospheres are blasted into space by stellar radiation. Yet there's a strange beauty in this destruction. As the sun expands, its outer layers will cool just enough for complex molecules like carbon and silicon to condense, creating swirling clouds of cosmic soot. These particles will eventually be blown into space, seeding future generations of stars and planets with the heavy elements forged in the sun's death throes. In a way, the same fire that consumes Earth will one day help build new worlds. Humanity won't be around to witness this final act. Our species will likely be extinct or evolved beyond recognition long before the red giant era begins. But the sun's fate is a reminder that even the most stable-seeming parts of our universe are temporary. The same star that gave us life will one day take it away, not out of malice, but simply because that's how the cosmic story unfolds. Every sunrise we see is a fleeting gift, a brief moment in a cycle of creation and destruction that spans billions of years. Here's something that sounds impossible at first glance. The edges of our universe are racing away from us faster than the speed of light. Not just a little faster, billions of light years away. Galaxies are disappearing over a cosmic horizon as space itself stretches faster than any beam of light could hope to chase them. This isn't science fiction, and it doesn't break Einstein's laws. In fact, it's one of the most profound revelations of modern cosmology, that space itself can expand at any speed it wants, because expansion isn't movement through space, it's the stretching of space. Let's untangle this cosmic paradox. Einstein's theory of relativity sets light speed as the ultimate speed limit. Nothing with mass can ever reach it, let alone surpass it. But relativity's rulebook applies to objects moving through space, not to space itself. Think of it like a loaf of raisin bread baking in an oven. As the dough expands, the raisin's galaxies don't move through the dough's space, they're carried apart as the dough stretches. Now imagine two raisins near the edge of the loaf. If the dough expands fast enough, they could separate faster than a hypothetical raisin speed limit. But neither raisin is breaking any rules because they're not actually moving on their own. This is exactly what's happening on a universal scale. The farther apart two galaxies are, the more space lies between them, and the faster that space grows due to dark energy's relentless push. At a certain distance, about 14 billion light-years away, the expansion rate crosses a critical threshold. Space between us and those distant galaxies stretches faster than light can bridge the gap. Those galaxies aren't vanishing, they're simply trapped behind an event horizon created by the expansion of space itself. Their light, no matter how bright, can no longer reach us, like a swimmer fighting a current that's pulling them away faster than they can paddle. But here's the twist. This doesn't violate causality, the principle that no information or influence can travel faster than light. Those galaxies aren't sending anything to us, they're being carried away by the fabric of reality stretching. It's as if the road between two cities is elongating faster than a car could drive, but neither city is breaking any traffic laws. This distinction keeps relativity intact while allowing the universe to grow at speeds that defy everyday intuition. What's mind-bending is how this reshapes our cosmic future. As acceleration continues, more and more galaxies will slip beyond our view, their light stretched into invisibility by the expanding universe. Billions of years from now, civilizations born in Milky Way remnants might look up and see only blackness, with no evidence other galaxies ever existed. The universe won't just feel empty, it'll be empty for all practical purposes, with every star, every atom, forever isolated by the relentless stretching of space. Yet in this grand expansion lies a clue to the universe's origins. The same physics that lets space outrun light today also explains how the entire cosmos could have inflated from a speck smaller than an atom to macroscopic size in a fraction of a second after the Big Bang. Cosmic inflation, a theorized period of exponential expansion, likely operated on the same principle, stretching space so fast that regions now billions of light-years apart were once in causal contact. Without this faster-than-light expansion, the universe wouldn't look as uniform as it does. There simply wouldn't have been time for heat and light to spread evenly. So while it's tempting to think of light speed as an unbreakable barrier, the universe reminds us that reality has layers. Space doesn't play by the same rules as the objects within it. It can stretch, twist, and grow at any speed it pleases, carrying galaxies, light, and even time itself along for the ride. The next time you hear that nothing can go faster than light, remember, the universe itself already is. Every atom in your body, the calcium in your bones, the iron in your blood, even the gold in your jewelry was forged in the heart of a dying star billions of years ago. When Carl Sagan said, "We're made of star stuff," he wasn't speaking poetically. He was stating a scientific fact. The carbon in your cells, the oxygen you breathe, the nitrogen in your DNA, none of these elements existed in the early universe. They were cooked up in stellar furnaces and scattered across the cosmos in violent supernova explosions, each one a cosmic assembly line for the building blocks of life. Take a deep breath. That oxygen filling your lungs, it was likely born in a massive star's final moments when its core collapsed under its own weight, triggering a cataclysmic explosion brighter than an entire galaxy. In those searing temperatures reaching billions of degrees, nuclei fused together at breakneck speed, creating elements like magnesium, sulfur, and silicon. The shockwave from the blast hurled these newly minted atoms into space at millions of miles per hour, where they eventually drifted into interstellar clouds like the one that birthed our solar system 4.6 billion years later. Now flex your hand. The iron coursing through your veins tells an even more dramatic story. Iron is stardust with a death wish. It's the element that kills stars. In a star's core, fusion builds progressively heavier elements, but the process stops at iron. Unlike lighter elements, fusing iron doesn't release energy. It consumes it, starving the star of its power source. When enough iron accumulates, the star's core implodes in seconds, triggering the supernova that seeds the universe with heavier elements like gold, platinum, and uranium. Without these apocalyptic explosions, Earth's core wouldn't have the nickel and iron that generate our protective magnetic field, and life as we know it wouldn't exist. Here's the most humbling part. The atoms inside you aren't just from stars, they've been stars. Some carbon atoms in your skin might have cycled through multiple generations of stars before landing in a primordial dust cloud that became Earth. Others could have spent eons drifting between galaxies before finally becoming part of you. Your body is a mosaic of cosmic history, with every element carrying a resume written in supernova, neutron star collisions, and perhaps even the Big Bang itself. This connection isn't just metaphorical, it's measurable. Modern telescopes can observe newborn stars surrounded by disks rich in the same elements found in our bodies. Mass spectrometers can trace the isotopic signatures of meteorites back to specific types of stellar explosions. Even the gold in your wedding ring can be chemically linked to the violent mergers of neutron stars, events so energetic they ripple the fabric of space-time. So the next time you feel insignificant under the night sky, remember, you're not just looking at the stars, you're looking at your ancestors. The universe didn't just create us, it literally became us. Every heartbeat, every thought, every dream is made possible by stardust that survived cosmic explosions, interstellar journeys, and billions of years of chaos to end up here, now as part of you. You're not a bystander to the cosmos, you're its latest, greatest experiment in turning starlight into consciousness. From galaxies drifting beyond the cosmic horizon to diamond planets and black holes humming subsonic lullabies, the universe has shown us its capacity to defy every expectation. We've explored how time bends like taffy, how the atoms in your hands were forged in stellar explosions, and how the moon quietly inches away each year, proof that even the most familiar corners of reality are anything but static. These truths aren't just trivia, they're humbling reminders that the cosmos operates on scales and rules that stretch our imaginations to the breaking point. Consider this, you're standing on a speck of rock orbiting an ordinary star, in a galaxy that's one of trillions, yet you're also made of the same stardust as those distant suns. The universe isn't just out there, it's woven into your very cells, a connection as intimate as it is incomprehensible. And while we've uncovered breathtaking mysteries, From dark matter's invisible grip to quantum particles whispering across light years, every answer unveils new questions, deeper layers of wonder waiting to be peeled back. So where does this leave us? Not small or insignificant, but awake. The universe doesn't diminish us, it invites us to marvel, to question, to push further. Whether it's through a telescope, a physics equation, or simply staring up at the night sky with fresh eyes, the adventure of discovery belongs to everyone. If today's journey through these cosmic surprises left you dizzy, imagine what we'll uncover tomorrow. Want to keep exploring the edges of reality? Hit like, subscribe, and join us as we dive deeper into the universe's greatest enigmas. The next revelation might be just a click away, and trust me, the cosmos has plenty more surprises up its sleeve. Stay curious, stay amazed, and remember, the universe isn't stranger than we imagine, it's stranger than we can imagine. See you in the next cosmic chapter.